All right, we're going to jump right into an idea that seems to completely shatter one of the most basic rules of physics. You know, the one rule you probably learned in school and never ever thought to question. And the question is just this: can anything in our universe actually move faster than the speed of light? I mean, your gut instinct and everything you've ever heard about Einstein probably screams, no, of course not. It seems like a pretty open and shut case, right? But what if it's not? Because, and you're gonna have to stick with me on this, the answer is yes. Kinda. Now, to be clear, nothing can travel through space faster than light. That speed limit is still very much in effect. But things can, and absolutely do, recede from us faster than light. And this isn't some sci-fi fantasy. It's a real fundamental part of the universe we live in. And hey, don't just take my word for it. This isn't some wild, fringe idea. Here's a quote from a really important paper by cosmologists Tamara Davis and Charles Lineweaver. They put it right out there. We can literally see galaxies that are, and always have been, moving away from us faster than light. So, what's going on? How is that even possible without just breaking all of physics? Well, the secret to this whole puzzle isn't in the things moving through space, but in the nature of space itself. It all boils down to the difference between two famous theories of relativity. And here's the absolute key. Special relativity, that's the one with the famous cosmic speed limit, it applies to objects moving through the fabric of space. Think of it like the speed limit on a road. But general relativity, Einstein's other masterpiece, is about the road itself. And it tells us that the road, the fabric of space-time, isn't just sitting there. It's a dynamic, stretching, expanding thing. So those faraway galaxies, they aren't breaking the speed limit. The actual road of space between us and them is stretching out from under them. And we have undeniable proof of this stretching. It's called cosmological redshift. So picture a beam of light traveling for billions of years to get to us. As it travels, the space it's moving through is constantly expanding. That expansion literally pulls on the light wave, stretching it out. And the longer its journey, the more it gets stretched, which shifts its color toward the red end of the spectrum. Now, this is super important. It's not the same as the Doppler effect, you know, like when an ambulance siren changes pitch as it passes you. That's about motion through space. Redshift is the evidence of the expansion of space itself. You know, the classic way to picture this, and it's classic for a reason, is the balloon. Imagine you take a balloon and draw a bunch of dots on it. Those dots are our galaxies. Now start blowing up the balloon. The dots themselves aren't running around on the rubber, but the distance between them just keeps getting bigger and bigger, right? That's because the surface of the balloon, space-time, is stretching. Now, what if you could blow up that balloon so fast that two dots on opposite sides are moving apart from each other faster than a tiny ant could crawl from one to the other? That's our universe. The galaxies aren't going anywhere. The space between them is just expanding like crazy. So this constant expansion has some really fascinating, kind of mind-bending results. It creates different types of cosmic horizons or boundaries out there in the universe. Let's try to make sense of them. Okay, so let's break down these cosmic boundaries. First, you've got the Hubble sphere. That's simply the distance from us where space is expanding away at exactly the speed of light. But it's not a wall or anything. We can and do see things beyond it. Then there's the particle horizon. Now, that's the edge of what we can see. It's the absolute farthest distance light could have possibly traveled to reach us since the beginning of the universe. And finally, the event horizon. This one is the real point of no return. Any galaxy that crosses it today will send out light that will never ever get to us, because space between us and them will be expanding way too fast for that light to ever catch up. So where is this boundary where things start receding faster than light, this Hubble sphere, right now? Well, based on everything we know about the universe, it's at a distance that corresponds to a redshift, which astronomers just call Z, of about 1.46. So any galaxy we spot with a redshift higher than that number is, at this very moment, moving away from us faster than light. And here's the absolute kicker. Astronomers see this stuff all the time. It's routine. Projects like the Hubble Deep Field have found tons of galaxies with redshifts way, way higher than 1.46. Some of the most distant ones have redshifts over 6. What that means is we are regularly seeing light from galaxies that were already receding from us faster than light when that light first began its journey to us, and they still are today. It's just wild. For a long, long time, the story of our universe seemed pretty straightforward. You know, the Big Bang happened, everything is expanding, but the gravity from all the stuff in the universe is pulling it back in, acting like a cosmic brake. But then, in the late 1990s, the story took a sharp turn nobody saw coming. The road to this discovery really began way back. In 1912, Henrietta Leavitt gave us a brilliant way to measure cosmic distances. Then, in 1929, Edwin Hubble used her work to prove that the universe was, in fact, expanding. And after that, for the next 70 years or so, pretty much everyone just assumed that expansion had to be slowing down. Then came 1998. And the key to the whole thing was a very specific kind of exploding star, a Type Ia supernova. These things are amazing because they are what astronomers call standard candles. Basically, they always explode with the exact same amount of brightness. So if you know how bright something really is, you can figure out how far away it is just by seeing how dim it looks from Earth. It's like knowing all light bulbs are 100 watts. The dimmer ones must be farther away. So a couple of teams of astronomers went looking for these cosmic lighthouses in the really distant universe. And the expectation was totally clear. They figured they'd find that these distant supernovae looked a little brighter than they should, which would prove that the expansion was faster in the past and gravity was successfully slowing things down. But what they found was the complete opposite. The supernova were dimmer than they were supposed to be. And that could only mean one thing. They were even farther away than anyone had calculated. For them to get that far away, the expansion of the universe couldn't be slowing down. In fact, it had to be speeding up. The universe wasn't hitting the brakes. Somehow, it was hitting the gas. This discovery was an absolute bombshell. It completely upended cosmology. I mean, if the expansion is accelerating, there must be some kind of mysterious force pushing everything apart, something that's winning the fight against gravity on the largest scales. So scientists gave this mysterious something a name. And they called it dark energy. And really, it's just a placeholder. It's the name we give to whatever is causing this acceleration. It behaves like this weird anti-gravity, a repulsive force that's pushing space-time itself apart. And right now, it is the single biggest mystery in all of physics. And just look at how dominant this mystery is when we add up everything in the universe, all the stars, galaxies, planets, you, me, the stuff we're actually made of. That's only about 5% of the cosmos. About 27% is dark matter, a whole other mystery, and a whopping 68% of the entire universe is this unknown dark energy. We literally live in a universe that is almost entirely made of stuff we can't see and don't understand. So what could it be? Well, there are a few leading theories out there. Maybe it's an energy that's just inherent to empty space itself, what some people call vacuum energy. Or maybe it's some new kind of energy field filling the universe, something they call quintessence. Or maybe our whole theory of gravity is just a little bit wrong on these immense cosmic scales. The truth is, right now, we just don't know, and finding out is one of the biggest quests in science today. This image really captures our entire cosmic story beautifully, doesn't it? From that initial hot, dense Big Bang through the era of stars and galaxies forming, all the way to today, where this mysterious dark energy is pushing everything apart into some unknown future. We have figured out so much, yet the biggest character in the story is still a complete mystery. And all of this brings us to one last really deep question. We've been talking about horizons, right? The edges of what we can see. But if space itself is the thing that's expanding, and it might just be infinite, does the universe as a whole even have an edge, or does it just go on forever? It's a question that reminds us that no matter how much we learn, the universe is always just a little bit bigger and a little bit stranger than we can possibly imagine.